Hello everyone, my name is Monika Trimoska and I will be presenting the paper XOR reasoning for the index calculus attack. This is joint work with my supervisors Sorina, Ionica and Gilles Dequen, and we are all from the University of Picardy in France. In our paper, we studied the use of SAT solvers in cryptanalysis. This field is commonly known as logical cryptanalysis, and thus we will start the presentation by explaining a bit how this method works. After that, we will mostly focus on the XOR operator, as this operator is extensively used in cryptography. I believe this is the reason why there has been significant research efforts in combining XOR reasoning into SAT solvers in the past years. And these XOR-enabled SAT solvers use a special form which is a mix of OR constraints and XOR constraints. It is always a better idea to use this form instead of transforming the XOR constraints into their equivalent CNF, because with this form we can use algebraic solving techniques such as Gaussian elimination, and these techniques have been shown very powerful in solving these types of systems. However, in our work, we have detected a use case where a Gaussian elimination in SAT solvers is not as efficient as Gaussian elimination in algebraic techniques, and then we have found a way to solve this. So we will continue by presenting our SAT solver, which is built from scratch and is DPLL based. Our solver is comprised of three modules: the CNF module that does the unit propagation as you know it, and two XOR reasoning modules. After presenting our solver, we will present our preprocessing technique, which is inspired from graph theory. More specifically, we will show you how we use the minimal vertex cover problem to decide on the order of branching variables. At the end, we will show you our experimental work, which is mostly focused on the elliptic curve discrete logarithm problem. This problem is at the core of many public key cryptographic systems. There are many ways to attack this problem, one of which is the index calculus, and the index calculus attack goes in three phases. One of these phases can be reduced to solving a Boolean polynomial system. This system is usually solved using algebraic techniques such as Grosvenor basis, but in our work we have tried to replace Grosvenor basis with our SAT solver. Our experimental work shows that our solver is more efficient than Grosvenor basis for this problem, which was the main goal of our work, but it is also more efficient than state-of-the-art SAT solvers for this particular problem. Now let's get on with the technical presentation. So as we mentioned earlier, in our work we studied the use of SAT solvers in cryptanalysis. So we will start by explaining a bit what cryptanalysis is. We will introduce characters that are usually used in cryptographic protocols. You normally have Alice and Bob that are that want to communicate through a channel that is considered unsecure. And so in that case they share a secret key, and then you have Alice that wants to send a message to Bob, so she will encrypt this message using the shared secret key and then send it through the channel, and then Bob can decrypt the message upon arrival. Now in this paradigm we have another character, Eve. She is eavesdropping on the communication channel and is trying to infer some information either on the secret key or on the message. So in this case, let's take, for example, the example of algebraic cryptanalysis, where Eve is transforming the problem of finding the secret key into a polynomial system. And then she's solving the polynomial system and she finds the secret key. So this is the process of cryptanalysis. However, in this case, we have depicted Eve as a good character because she does not have any bad intentions. The cryptanalysis in academia has a purpose of verifying whether the crypto system is secure enough. So in this case, if we manage to break the crypto system, this just means that we have to use bigger keys, we have to change the size of the key, or in some cases, if Eve finds an algorithm that can find the secret key in less than and is less than exponential, then this means that we have to actually change the entire crypto system. With logical cryptanalysis, it is the same. This is the case where we use a SAT solver to aid in the cryptanalysis process. So in order to use a SAT solver to solve this polynomial system, we need to first rewrite this polynomial system as a propositional formula. Now, SAT solvers usually take a CNF. However, as we said, it is often beneficial to keep the XOR constraints in the system. So we will first explain how to go from a Boolean polynomial system into an algebraic normal form. This is a very simple process because as we are working with Boolean variables, the addition simply becomes the XOR operator and the multiplication becomes the logical AND. However, most SAT solvers are not adapted to read this type of conjunctions, so we need to replace the conjunction. We need to replace the conjunction with a newly added variable that we will call x prime. We still need to keep all of the constraints in our system, so we need to keep the constraint that x prime is equivalent to x2 and x3. This equivalency is further transformed into three OR constraints using the following technique detailed here. Now, this is how we go from an ANF formula into an equivalent CNF XOR formula. All occurrences of conjunctions are replaced with a newly added variable, and then we also keep these constraints in our system that explain the equivalency. Now, in this CNF XOR formula can further be transformed into a pure CNF formula, but this is a very classical process and we will not explain it here. Our solver is adapted to read both INF formulas and CNF XOR formulas. Now, there exist solvers that are adapted to handle XOR constraints and also that perform Gaussian elimination. However, we have detected a case where Gaussian elimination is not as efficient in SAT solvers as in algebraic solving techniques. More specifically, we have detected a case where a possible cancellation of terms is overseen due to this CNF XOR formula or due to the way that SAT solvers are implemented. Let's look at this with an example. So let's say that in this case, we want to set x2 to 1, or respectively in the CNF XOR formula, we want to set x2 to true. Now, what happens on both sides? So on the left, we have the variable x2 is cancelled out because this whole term x2 times x3 will be equal to 1 only if both terms are equal to 1. So now that we know that x2 is equal to 1, x2 doesn't matter anymore. The value of this term depends only on x3. On the right, as per unit propagation, for example, we will delete this first clause because it is already satisfied by the variable, the literal x2. In this last clause, we will just delete this literal because it cannot satisfy the clause. So now in the simplified systems, we have this situation. So on the left, if we XOR the two equations, we will infer that the value of x1 is 1. So this is the technique of Gaussian elimination. However, on the right, we cannot infer anything, looking at this formula, we cannot infer anything on the value of x1. So this is a missed opportunity to propagate another variable. We have found a way to fix this in our solver. We have just defined the following rule, which seems very straightforward. However, it is not implemented in SAT solvers due to the form. So anytime we set a variable to 1, we verify if we have the following rule, and if we do so, we replace all occurrences of x prime in this case by the variable x3. Now we'll give some more details about our SAT solver. So as we said earlier, it is DPLL based, and as such it works by recursively building a binary search tree. This is done by assigning truth values to variables and then doing a backtracking procedure whenever a conflict occurs. In the case where there is no conflict until the last branch of the tree, we decide that the formula is satisfiable. So our solver is comprised, as we said, of 3 modules. These reasoning modules, they are always synchronized. They work together to propagate variables, and they all have their own propagation rules and their own backtracking procedure. Now, the CNF module is unit propagation on OR clauses. It is the classic unit propagation as you know it. The XOR set module also adopts a unit propagation reasoning, but it is adapted for XOR clauses. So this is based on parity reasoning. When there is only one variable in the clause left, the value of this variable can be inferred through parity reasoning. The XORGAUSS module is the one that actually implements the Gaussian elimination that makes the solver so efficient. And so we will explain a bit about how this XORGAUSS module is implemented in our solver. So to do this, we will use the example from before in algebraic normal form this time. So the XOR clauses in our solver are implemented as equivalence classes. This means that we take each clause and then we choose a representative for this clause. For example, here we chose x1, and then we describe the equivalence class as such. We say that x1 is equivalent to the rest of the clause, keeping in mind that we should flip the constant. So now each occurrence of x1 in the following clauses should be replaced by the right side of the equivalency. Here we don't have such an example. When we finish the first clause, then we do the same with the next clause and the next and so on, so we get this minimized system. Now, at an implementation level, our equivalence classes are represented as bit vectors. And so we have shown here an illustration of how this works for our example. So in the bit vectors, there is 1 bit for each variable and 1 for the true-false constant. And so for example, when there is an occurrence of this variable in the equivalence class, we set this vector to, we set this bit to 1, and when otherwise we set it to 0. And these bit vectors are stored in an array indexed by their representatives. So this representation allows us to do all Gaussian elimination operations and all substitution operations just by XORing these bit vectors, and it is more efficient this way. Now we also have a preprocessing technique that is derived for Boolean polynomial systems that are solved using SAT solvers. Now we will first, this preprocessing technique allows us to choose the order of the branching variables. So let's first give the motivation of this work. Now when solving polynomial systems that are not linear, our main goal is to get to a state where the system is a linear system, and then it can be easily solved using Gaussian elimination. So to this end, for example, in the example here, if we first start branching the tree with the variable x1, we have done absolutely nothing because to get faster to our goal, because x1, as you see, is not in any term that is of degree higher than 1. So the degree of the system doesn't the degree of the system is unchanged if we assign x1. So this means that when solving this system, there is an order of branching variables that can be more efficient than another order. So to find this order, we used the MVC, the minimal vertex cover problem from graph theory. We will explain how. So we take a Boolean polynomial system, and then to represent it as a graph, we have each variable to be a vertex in the graph, and then an edge in the graph is written if we have a term containing both vertices in the edge. So for example, here we have a multiplication of x2 and x3. So we have an edge between x2 and x3. So now imagine if we find the minimal vertex cover of this graph here. Now just recall that the minimal vertex cover is a subset of vertices in which for every edge in the graph, either one of the extremities of the edge is in the vertex cover. Okay, and the minimum one is the one that has the least vertices in it. So here we have found that the minimal vertex cover is x2, x5, and this tells us that if we give a value to x2 and x5, this means that they will disappear from the system because they will be assigned, and with them all of the edges that are connected to these vertices. And see that if we do this, we obtain a graph that has no edges left. What does this mean? This means that if there are no edges left, there is no multiplication left in the corresponding system. So the system became linear. So we will decide on the branching order. Here it will be x2, x5, and then the system is linear and it is solved. Our experiments are focused on the discrete logarithm problem. We will shortly define. Our experiments are focused on the discrete logarithm problem. We will shortly define it here. Now, we have an elliptic curve. The elliptic curves are extensively used in cryptography, and we have an elliptic curve that is, for example, defined by the following equation. This is the case that we study in the paper, because there are different types of elliptic curves defined over different types of groups. So every elliptic curve, there is an additional law that is defined on that curve, and it is shown in this illustration here. Now, if there is an additional law, this means that if we can add points together, we can also define a discrete log problem for this curve. So the discrete log problem is defined this way. We have 2 points on the curve, the P and Q, and so we need to find how many times P has been added to itself in order to obtain Q. So we need to find the scalar X here. So this elliptic curve discrete log problem can be solved using different algorithms. You have the generic methods that are able to solve the discrete log for elliptic curves over any field, but you also have the index calculus attack, for example, that cannot be used for every group. This is the attack that we are working on for this paper, and so this index calculus attack goes in 3 phases, one of which is the point decomposition phase. This is the one we are concentrating on. This means that we want to have a random point on our curve, and we want to find, we want to be able to decompose this point in other a given number of points. So this is the part of the attack that can be reduced to solving a Boolean polynomial system, and so it can be solved using a SAT solver. Now we have, in our experiments, we have 2 different models. The first model is the one where we try to decompose a point into different points. And so we have tested this model against the Grobner-Bessis algorithm, the F4 algorithm implemented in Magma, and against other SAT solvers. So you have state-of-the-art Minisat, Glucose, and Crypto Minisat, and then the 2 winners of the last SAT solving competition. And then you have our new solver here at the end. So as you can see in these results, the solvers that are not adapted for XOR reasoning didn't manage to solve the model didn't manage to solve these instances in the given time frame. However, Crypto Minisat with Gaussian elimination enabled did manage to solve it, as well as our solver with Gaussian elimination. However, our solver turned out to be more efficient for this particular problem. The next model is a model where we decompose a point in 3 different points. So the derived model is very different from the previous one. And one big difference is that for this model, the Gaussian elimination didn't turn out to be very beneficial. This can be explained if we look at the number of conflicts, which you don't have here in the slide, but you can compare them in the paper. The number of conflicts is only slightly better when we turn on the Gaussian elimination, and performing these types of operations has a great computational cost, so it is better to use our solver with the Gaussian elimination turned off. It still outperformed all other approaches for solving this model. So in conclusion, we have found an oversight in XOR-enabled SAT solvers, and we have shown a method how to fix this. We have successfully managed to replace Grobner basis techniques for solving the index calculus attack on binary elliptic curves. And also our proposed solver turns out to outperforms all existing resolutions for this particular problem.